I would like to welcome you all to the first talk of this year's Jones Seminar Series. And I am very happy to welcome Professor Karen Smilowitz, who is our first Jones Seminar speaker. And I will say a few words to introduce her. So Karen is the James N. and Margie M. Krebs Professor in Industrial Engineering and Management Science at Northwestern University. She's an expert in modeling and solution approaches for logistics and transportation systems in both commercial and non-profit applications, working with transportation providers, logistics specialists, and a range of non-profit organizations. She's the founder of the Northwestern Initiative on Humanitarian and Non-Profit Logistics and has been instrumental in promoting the use of operations research within the humanitarian and non-profit sectors through the Woodrow Wilson International Center for Scholars, the American Association for the Advancement of Science, and the National Academy of Engineering, as well as various media outlets. She's an associate editor of Transportation Science and Operations Research. She has won many awards, including the award for the advancement of women in OR and MS fields, as well as being on the winning team for the Innovative Applications of Analytics Award. For her work on data visualization for mass participation events. So with that, please join me in welcoming her for this seminar.
Thank you. Can you hear me? Because I can't stand at a podium when I give a talk. Also, I asked Vikrant if people ask questions throughout, and he said, no, not really, but I would like you to ask questions. If you're in these two rows. Beyond this row, my neck is going to kill me by the end, so if you also want to move down, I would appreciate it, because I really am short and I can't see any of you up there. So come on down if you'd like to ask a question. When you ask a question, come down. No, I'm just kidding. Well, I do want you to come down, but I do want you to ask questions too. The work that I'm presenting today is a little bit of a pet project of mine. It was a history project. So I do a lot of work on transportation for public school systems. And as I'll show in a few slides, I started getting interested in this question of the intersection between operations research and public policy and on some of the court cases around public school design, network design. And so I gave this talk in Australia this summer when Vikrant and I were at a conference, and he said, we've got this Jones seminar, and I think this would be great. So I'm really excited when I heard about the Jones seminar, and I thought this would be really fun for me to come and give this talk here. So thank you. So that is why the work says it's motivated by this collaboration. It's kind of something that I started working on because of the work that we're doing. This is an amazing team. There's a lot of names here. We've been working with the public school system in Evanston and Skokie for a couple of years now. A ton of PhD students, Li Wei and Paul most notably, my faculty collaborators, Sunil and Jill, and then a ton of amazing undergraduates. Depending on how we do on time, I'd love to show you some of the work that the recent students are doing. And of course, want to thank our wonderful sponsors for supporting this work. Any questions so far? I figured one question that might come up, given the broad range of the audience, was what is operations research? It's cutting off the top over there, but it says, what is operations research? So I asked Vikrant, I said, should I start with a few slides? So how many of you are aware of operations research? A bit? Okay, good. So I'm going to go now. So operations research is, the way that I describe it, is the development and application of quantitative methods for decision making. And I think those two words are really important, and that's really what I want to talk about today. Is sort of part of what we do is a lot on developing these tools, modeling tools, solution methods, statistical methods. But another big part of what we do is applying the methods. And so this is a slide that I adapted from my colleagues, or former colleague now, Wally Hopp and Ajit Tamahani. That kind of shows the evolution of operations research over time. And if it's not too cut off at the top, this idea that this is a field that's really driven by applications to make changes to the methodologies that we have. And so this slide kind of shows, as we've gone through different areas in which operations research has been applied, you've seen a different set of tools evolve. And so if you've seen the movie Cheaper by the Dozen, maybe not? Some of you are too young to have seen that. But that's kind of the time and motion studies, right? So at the beginning, sitting in a factory with a stopwatch, and that's kind of where the field operations research, industrial engineering started. And then kind of as we move into looking at quality control, military in the 50s was a lot of the work in optimization, and then transportation, which is our field. You can see how not just as the applications where we apply our methods evolve over time, but the methods themselves evolve. And so I think that for, as Vikrant mentioned, the work that I do is in humanitarian and nonprofit logistics. And the work that my students and I do are thinking about, like, well, what do we need to do in terms of changing the methods we have to address these problems? And that kind of brought me to the work I want to talk about today. So this is the public school district. Northwestern's right here on the lake. And this is the school that my kids go to right there. And this work just started because as a parent, they were going to cut some of the school buses to where my kids live. And if you can see here, this is a pretty busy street, and that's a pretty busy street. And so I said, well, I have a background in civil engineering. I can get some laptops and parents so we can count cars. And this kind of evolved into this larger study where we started looking very broadly at transportation throughout the district. And when we looked broadly, we started looking at this problem called the school bus routing problem. And when we would give presentations or have our literature review, we kind of had this sentence that said, this has been studied in the operations research literature for over 50 years. And that kind of got me back to that prior slide. You know, thinking about, well, what was going on to motivate the emergence of the school bus routing problem? And that's really what I want to talk about today. My neck is killing me. Are you sure no one wants to come down? I am 5'2" on a good day, and y'all are really high. So that kind of got me thinking about kind of how do we link what was going on in the country 50, 60 years ago, and how was operations research contributing? I was also very interested in this question of what could we do in operations research 50 or 60 years ago. We didn't have the laptops that all of you have here. When you wanted to run an optimization model, you had to buy computing time. And so when we think about limitations in computing power, back then we were also thinking about limitations in funding to purchase time on the computers to have the computing power. So I was kind of curious how this all worked together. So I'm going to give you, and again, I am an engineering professor, so anyone, again, not just questions, but you want to, those of you who are legal scholars in the room can join in as well, because I'm going to give you a super brief overview of school desegregation in the United States in 3 minutes. So Brown versus Board of Education in 1954 was the ruling by the Supreme Court that ended separate but equal in terms of education, right? So this was what's known as de jure segregation, so segregation by law, meaning that you could not argue as a school district that we could have two different schools, and as long as they were equal, they could remain separate, right? So what Brown versus Board of Education did is said that is no longer the policy of the United States in terms of public education. Then what was known as Brown 2 said, okay, speed it up. We're going to do this, but we're going to do this with all deliberate speed. And you can see this was taking a while, right? You're trying to end segregation of schools. Whoops. Went the wrong way. Okay. So then you see more court cases that said desegregation now. And so at this point, you started to see operations researchers think about, well, how do we do this? How do we help school districts? Because clearly it's taking a lot of time. Now, I'm not going to argue that the lack of mathematical skills is what was keeping this going on, but that's not my main point today. But how can our understanding of mathematical models help in this way? And so where a lot of the work started coming in modeling is when you get rid of de jure segregation, what's left is de facto segregation. So de facto segregation is segregation that results from societal differences, right? And so when you think about schools, and I showed you the map over there, if you think about residential neighborhoods. Actually, let me go back to the map for one quick second. Oh, that went really fast. This is Evanston. If you can look really quickly, if you're really quick at picking up names, there are N schools. These are our neighborhood schools. So this is at the K through 5 level where kids attend their neighborhood school. There are N schools, and there are N+1 rectangles. So what Evanston did to desegregate our schools is this is an area known as the 5th Ward. The school in the 5th Ward was closed, and then kids were sent to 5 different schools. So this is kind of what was done, and I'm going to talk about some of the work we're doing around that now. But what happened in this Swann versus Charlotte-Mecklenburg case was looking at how neighborhood patterns were leading to school segregation. Right? So once you got rid of legal school segregation, then residential segregation became an issue. And so the argument became, well, what can we do to overcome residential segregation to desegregate our schools? And this is where operations researchers got in. I will talk, and we'll see how we're doing on time, of kind of what has happened recently. So there has been a pendulum swing now saying that you can no longer use race to design your school district. So a lot of the models that I'll show you initially are models that are no longer legal in terms of how you design schools. And I'll talk a little bit about different ways that's being done at the moment. Questions so far? Was that a very quick? Okay. So what was happening in operations research at the time? Two very important streams of research that I want to talk about. One was the work around these location models. So also related to what was going on in the courts at the time was looking at how do we draw political boundaries? How do we do voting districts or political districts? And so looking at how do you come up with ways, we've obviously, I could talk about that subject for a long time now. But what I want to really pull from that was this idea of using sum of distance squared to try to create these compact regions for voting. So that's kind of one stream of research. So looking at how do we partition space with some idea of a distance metric, right? So you can kind of think about where we're going to in terms of school districts, right? We want some way to take some large geographic area and break it up into smaller geographic areas, and we want these areas to be somewhat compact. So that's going on the political districting literature. It's also going on with dividing up warehouses, what regions warehouses would serve, things like that. There's also the transportation problem. So the transportation problem, simply put, is I have some sources and I have some destinations, and I have to flow goods from source to destination, and I want to do it as cheaply as possible. Now, this problem has a really nice property that I can solve it with continuous variables, and it solves very quickly. And back in the 50s and 60s, people were getting really good at solving this. So around that time, we've got a really good way of solving models of getting from A to B. You know, if I've got some items from A and some items from B, I can do that pretty quickly. So that's kind of where we were. And so when these court cases came out saying we need to desegregate schools now, operations researchers stood up and said, oh, well, we've got some mathematical models. What can we contribute to this? So I want to talk about, to some extent, how our limitations in computing power limited what could be done with this model. And then, at the same time, there were some very positive things that could happen as well. The language in the papers going back to the 50s is also very interesting. I won't talk too much about it, but there was one paper that I thought was really funny about, well, this is typically done by a man, and this paper is written by a man, or for that man. So I thought I appreciated that. I won't go into the rest of the wording in the papers. So the school redistricting problem is that you want to find a capacity-feasible assignment of students to a school. So when you think about this problem, think about, you've got these geographic units, right? We're not looking at individual students because we want to have solutions that are going to go on for 20, 30 years. So you want to think about, how do I partition space into schools, into regions served by a school? So your decision variables are some sort of geographic unit. So it could be a street segment, it could be a block, it could be a census tract. Now, what I'll show in a little bit is computer power was not great back then, and so these units tended to be quite large. And that caused some problems in the resulting solution, because you couldn't really solve it. When we look at the problem now, we've got these very small blocks that basically can be the north side of a street, the south side of a street, east and west, and that becomes your unit. In the 60s, you couldn't solve that problem. That would be way too hard. So a bunch of papers came out. You probably can't read it all right now. But this is from 68 to 75. Papers have started looking at, okay, how do we think about using what we can solve in terms of operations research problems, so linear programming approach, network flow approach, implicit enumeration, using the tools, linear programming, that we had at the time to solve these problems. So I want to show you how that was done, kind of how we went from what we could solve with the transportation problem to looking at school districting. So this is the transportation problem that I mentioned briefly. So the idea is I have a set of supplies, so we're going to call that set M. And at each one of these supply sources, I have a certain amount of supply. So C sub I is at a source I, how many units of flow do I have to give out? What is my supply? And then I also have some destinations, this set N, that have some demand. So, oops, that's a typo. That should say, no, that's right. Does it say PJ? Pretend it says PJ if it doesn't. But at destination J and N, how much demand do I have? And then my decision variable is going to be the flow. So this is Xij. How much flow goes from I to J? And then I have to decide what my objective is in the flow, and I'm going to say I want to minimize the cost of transportation. So I want to minimize Dij times Xij. So how much is going from I to J times the cost from I to J, and I'm going to sum over all my Ij. Right? Sound good? Good? Okay. So that's what this optimization problem is. So my objective function says I'm going to sum over I and J in my sets, how much I'm flowing with the cost of that flow. Good. My constraints are I can't send more than I have. So for every, so this upside down A, for all of you who have not seen that, that just means for all. So for all sources I in my set of sources M, the amount that I send when I sum over all my possible destinations cannot be more than what I have. I also need to make sure I meet all the demand of my destinations. So if every destination has a demand Pj, I have to make sure that what I flow into it is equal to Pj. I can also set it greater than or equal to Pj, and it will be satisfied at Pj because I want to minimize. And then my flows are non-negative and continuous variables. And this is critical. So back in 1950, there were great solution methods for solving this problem, given this assumption, right? When you have continuous variables, this is an easy problem to solve. Now, what I want to talk about is the implications in school design when you impose this constraint. So the other problem, now this has a bunch of other constraints, but they're not relevant. What I wanted to pull out from the political districting problem was this idea of using distance squared. Right? So the original problems looked at the distance, but when I look at distance squared, what it tends to do is create this more compact. It basically penalizes the assignment of far i's to far j's. You want to try to reduce that as much as you can. Good? Good summary of transportation problem? Okay, so now how do we translate that to the school districting problem? So let's say our sources are now going to become blocks. So over here, we're going to look at whatever, and blocks I'm really using for whatever this geographic unit is that we're partitioning space into, right? So it could be census tracts. Think about, with our mindset in the 50s or 60s, these are pretty large geographic regions at the moment. And then my destinations are going to be the schools. And then what I want to do is I want to assign blocks to schools. And then in the models, and this is what we'll talk about the implications of this, we're now going to take the blocks and we're going to break them up into subpopulations. So you can think about it as racial groups. You can think about it as ethnic groups. Some of the models now look at socioeconomic groups. So some way to partition your population in a block. And then rather than having assignment flows, now you have your decision variables. Make sense? Yep.
Next question. Mm-hmm. This is about the segregation. So the students does not have any choice model. So they do not get to choose where to go.
No. So there were no chosen schools. What I will talk about, when I talk about some of the later models, is there were some ideas about so right now we're just thinking about the neighborhood model. You're just assigning neighborhood. What was happening in districts like Berkeley was thinking about ways to use magnet schools or two-way busing to come up with better ways, because you'll see kind of the implications of this. But right now, you only think about the model of partitioning space into your neighborhood schools. Yep, good. Other questions? No? Okay. So this is what's known as kind of the kernel problem. So this was the first paper that looked at, one of the first papers. I chose this one over other ones because the notation's a little more simple. But the objective function is really the same as the objective function of the transportation problem, right? I just want to minimize the distance of the assignments that I make. Make sense? I have the school capacity. So looking at all of the blocks and all of the subpopulations in a block, making sure that I don't exceed the capacity of the school. I also have to make sure that every student is assigned to a school. And so now I'm thinking about for every block, I have to make sure that the flow or the assignment of students to schools is equal to the population. And then this is the way that in the early models, desegregation was addressed. So looking at these a priori bounds. Now, these are a priori bounds, meaning I don't know ultimately how many students are going to be assigned to that school, but I'm going to set some bounds on the number of students from each subpopulation group. Sound good? And when I say, so the models are described very broadly. Back in the time, you could really only solve it with 2 groups. That was really all the models could handle. And then we have these non-negative continuous assignment variables. So I'm going to use these assignment variables and think about how there's a paper in 91 that started going back and looking at these models on the way that this was done. So the model that I first showed you is what's known as track splitting by race. So think about how hard this is to implement. So look about this model. This model is basically saying, and think about this, what it does for neighborhood cohesion. I'm just saying some fraction go to this school, some fraction go to that school, and I'm also going to divide this again by subpopulations, and this is just going to all work. So this is what the early models did, because again, this is what the computer power did. I mean, this is what I'm assuming. I was not doing operations research models in the 60s. So that's the first set of models. A second set of models is really where we try to get to now, which is this idea that of, what's the word, splitting by space, that instead it really should be a geographic partition of the space, right? So now instead of having assignments by subpopulations within a group, it's everyone is assigned. If this is where you live, this is the school you go to. These are still continuous variables, right? And so, and again, these are still large units because we can't solve very large problems right now. So these are large geographic spaces. So in order to do this, they're making assumptions that the distribution across the subpopulations within the space are homogeneous. And so that, again, I'm going to show you some of the work that looked at why that is or is not a good assumption. And then kind of the gold standard of where you're really trying to get to and what is used now is the idea that you want these to actually be binary variables, 0, 1. Is this block assigned to this school? The problem is back in the 60s, we couldn't even solve the continuous version of this, let alone the integer version, right? And so you're trying to solve these large scale problems, and when you're trying to solve them with integer variables, it becomes much harder. So there's this paper that came out in 73, but in order to solve it, it requires a large number of simplifications. The other thing that we look at is the way that these balance constraints work. So one is what I showed you, which is the a priori bounds. However, when you start looking at these models, the number of students that are ultimately going to be assigned to a school is not necessarily known. And so so while you may set these bounds a priori, you don't know what's actually going to happen with the resulting model. So another version of this, which is what tends to be done now, is looking at bounds based on assignment. So, and I'll show you this one later. The goal in desegregating the schools is if you look at a town, what you would like is that every school in that town, the racial balance looks like the balance of the entire town, right? So if you have a population, if it's 60-40, every school should be 60-40. And so what these bounds do is they try to look at how do we come up with a way to look at the ultimate assignment. So if I can take this xijk hat for some school J and I sum it over all of the, sorry, this should not be summed over K. That's a typo. It should just be summed over M. No, it's not a typo. Sorry. My bad. This is K hat. So it's this in here is the total number of students assigned to that school. And so I want to make sure that no one group, I'll go to the upper bound because that makes more sense, no one group is more than, say, 60% of the population of the school, right? So you want to make sure that you're creating a more balanced population in your school. You can also look at the same sort of bounds based on assignment, but now this is when you do split by space. So this is the xij instead of xijk. So you're looking at assuming, again, this assumes homogeneous distribution of students in space, but you're saying what is the resulting mix of students? And then you can have that as well for the integer programming. Makes sense? So these two constraints are really the same. This kind of gets down to the nuts and bolts of the mathematical modeling, but they're essentially the same. It's just whether or not you allow the XIJs, XIJs to be continuous or not. Make sense? So this is kind of, you can now look at this in 2019 and say, well, obviously this is the set of constraints I would use and these are the assumptions I would make. But back in the 60s, think about what could actually be solved. So there was a paper in 74 that started looking at this question of, well, how do you model this problem? Right? What are the implications of the different assumptions? And so they looked at this very stylized school district and thought about, well, what happens on our assumptions of assignment variables, our assumption on the balance constraints, whether or not to use distance or distance squared, and whether or not to try instead to come up with two-way busing models. So two-way busing in Berkeley, the way that it was implemented or envisioned was, so think about what I showed you with the 10 schools in Evanston. So if you have K through 5 schools, now you're thinking of these smaller subdivisions, and so you have fewer students bused, but when you look at who is bused in Evanston, there are certainly some bias in how long you're on, whether or not you take a bus, and whether or not, and how far you're on the bus. The idea of splitting up into a K through 2 and a 3 through 5 is now you've doubled the radius around a school. So now more students are bused, and more students are bused greater distance, but the idea with these is to create more equity in the busing. So that's another thing that we'll look at. So kind of your question about what are the models. It's still neighborhood-based at this point, but thinking about different configurations. So what did they find? So one of the things they looked at is this assumption of homogeneous distribution in space. And so again, this is a very stylized example just to illustrate their point. But say we had 4 tracks. So here's 1, 2, 3, and 4. These papers are from the 60s, so I apologize that this is the best language in the papers that I could find you. Some of them are worse, so I will say that as an engineering professor, it is not a topic that we are necessarily comfortable talking about, but I think it's important. And so I may not say, may show you some things from the 50s and 60s that you're like, that is really not the way I would talk about this problem, but I think it's important we explore these problems, and I hope that you will bear with me and correct me wherever needed. But yes, this is how the tracks go, and so there's 3 schools, and you want to think about how you're allocating them. So this is an entire track, but they're saying that there are 85% of the students who are white live here, and the 15% of the students who are black live over here. So what does that mean? If you take this, what is this, a little cross here being the center of the track, if you separate it into subpopulations, what is the distance to the school? So when you look at just minimizing Dij, Xij, and you assume that there's continuous distribution, what ends up happening is the students who are bused to your school, there's very much a split based on race, right? And so if you don't account for the fact that the distribution within space is not the same, you're going to end up with large bias in how long students are on the bus, which is pretty much to be expected. Now, the way that you can handle this is looking at smaller and smaller block sizes where you can assume a homogeneous distribution. But back then, that's just not what could be solved. They also found that what you would expect, more aggressive racial balance constraints led to more busing. And this is where I want to show you from the court case is what operations research allows you to do is quantify the extent to which that's true. And so I'll show you a court case in which the district argued we cannot do desegregation because there'll be too much busing. We won't have neighborhood schools. And then the operations research model showed, no, you can. You can achieve what you say. And I think that that's really the point that I want to make with this. And that when I work with the school district to say, I'm not here to make the decisions. You are the school district. You make the decisions. I'm an engineer. But what I want you to do when you make these decisions is to really think about what you're saying and to think about what does this mean in terms of capacity? What does it mean in terms of busing? So our tools are your sandbox to play with. And so I think that when you think about these cases, this is what they looked at. The other thing, which I think is really interesting on the distance versus distance squared. So when you move from distance to distance squares in your objective function, you create more compact regions. And so what that does is it gets rid of the really long trips. It does mean that busing overall increases. So the travel distance increases. But that's not a bad thing. Because when you think about the cost, if you are busing kids from one neighborhood to one school, that's about as efficient as you can get, right? And so when you think about, I'll talk in a minute, two-way busing, taking students who live close, who are densely populated, that's good. And so we want to think about, having all the students in the district bused can be more efficient and more cost savings than just a subset of the students bused a really long distance, right? When you think about the economics of busing, it's the fixed cost of the bus. You want to fill up your buses. And so if you can do that, you can lower your costs. They also found, which I think some communities do really well, is think about two-way busing as a way to improve equity. So in terms of how students are bused across. So what does this mean for the courts? So this paper was just an academic study looking at at what was going on in the literature. There was a group at Berkeley that was specifically brought in to look at a case in the Bay Area. So this is Northern California. And this was looking at this idea of how do we use busing as a mechanism to end de facto segregation, right? So if we take a neighborhood that has residential segregation, can you use busing to desegregate the schools? So they looked at a couple of models that they could evaluate. So the first model is just the standard transportation problem. So no balance constraints. If we just opened up the district and said, let's minimize distance so that we have these nice compact regions, what would we come up with? Then they looked at the same model, but now they added racial balance constraints. The goal was to do balance based on assignment, split by race. That was really hard to do. And in the paper, again, think about this. This was a court case on trying to come up with a way to desegregate schools, and there was only so much they could do because of how much money they could spend on computer time. So that's kind of, again, how far we've come. So instead, they had to come up with Model 3, and so Model 3 is really a decomposition of Model 2, thinking about how to solve this problem. It's not great. And again, this is where, because we couldn't solve very large problems, there are assumptions in the way that the solution approach was designed that implicitly bias the solution. And I think it's really important as engineers to think about, in order to solve things, what are we doing? Right? There's a lot of work now in machine learning and this is a computer, everything's great, but think about what are the inherent biases. And I think this is an interesting case where just the inherent biases in the way that the solution method was constructed led to biases. And again, I don't want to fault these guys. These guys really were arguing that there were ways to do this, but even so, because of what you could solve, you end up with these problems. So this is from their case, if you can read this here, this is from the paper from the 70s. And again, this is how the racial balance, those limits were set up, those bounds, right? So the bound is that you want to try to devise school boundaries so that every school, the racial makeup of a school looks like the district, right? So these are kind of their goals set out to go. But what they ended up doing is they ended up, again, having to really solve it in steps. They couldn't solve the full problem. So what they would do is they would look at, well, let's solve for the neighborhoods that are more integrated, and then we'll go back and fill in capacity as needed, right? And so what ended up happening is that ended up creating further travel distances for some neighborhoods than others. And again, this is just because of the way that they could solve the problem. But here's kind of the interesting side of this, right? So think about this is going to be the proportion of non-black enrollment in the school and the percentage of black enrollment. This line here is a solution in which each school looks exactly like the distribution at the district level. Make sense? So if you perfectly desegregated the schools, your solution should go on this line. This line goes that way. This is residential segregation. So this is kind of, if you looked at how people lived, the distribution of housing patterns throughout the district, you get this line. This is current school segregation. This line right here is what the schools looked like at the time of the court case. This is Model 1. So Model 1 is if you ignored any racial balance constraints, what does your district look like? And this is what you come up with. And then this is what they were able to get with Model 3. which is pretty good, right? So this is thinking about how do we try to get as close as possible to this line. But what I think this also really highlights is kind of what was known at the time and is known today is kind of the issues with de facto segregation, that when we think about neighborhood schools, how do we come up with solutions like K through 2, 3 through 5 to get over what's going on with racial segregation or of housing? So the court case looked at what was happening with these newly built schools. So this was in Richmond, California. Richmond Unified School District was creating new schools, and a group of parents were suing the school district saying that the way that you were building these new schools is basically leading to de facto segregation and de jure segregation as well. So I'll show you the court ruling in a second. So these two professors in Berkeley were testifying on behalf of the families, the plaintiffs. The district had an expert who said, linear programming is not appropriate, but I don't know what linear programming is. So I like that. That's now the district district expert said, this is not acceptable. We have to have neighborhood schools, and neighborhood schools means everyone has to go to a school within 4 miles. So the plaintiff argued that you could do this. All right, so Model 3 was able to show that you can tell me it has to be within 4 miles, but I can achieve that. And again, this is where I think it's really the power of mathematical modeling, right? I'm not going to design your school district, but I think and this is, I think what you're seeing now with some of the work in gerrymandering, right? Is we're not going to tell you how to do your districting, but we can tell you this doesn't look right, right? Somehow there's no mathematical model would come up with this. And so this is from the actual court case. And so what's interesting is they, in fact, did find that the segregation was de jure, meaning that this was, in fact, legally, or they were using these new schools to come up with, to segregate the schools. And even if it were just de facto, they need to address it. And this is what that Charlotte versus Mecklenburg case said, that even if your segregation that results afterwards is de facto from residential segregation, the onus is still on you to address that. And then the last point I italicized, or they italicized in the paper, which I like, is you can do this. You can get within 4 miles and still desegregate your schools. So that was kind of, I'm going to pause here for a minute because then I'm going to move on to the future. But any questions on life in the 50s and 60s and 70s? Yep.
Sorry, would you mind just defining two-way busing?
Oh, yeah. So two-way busing is instead of taking, so think about you have 2 schools, right? I have one school over here that's going to serve all of you guys, and I have one school that's going to serve all of you guys. And so you in the middle, you're probably going to have to take the bus. You guys definitely, thank you for sitting close to me, so it hurt. But you're going to take the bus. Two-way busing says, now you guys are K through 2, you guys are 3 through 5, and everyone's going to bus probably, except for one school or the other. You're either going to bus for K through 2 or 3 through 5. Mm-hmm.
When they collected the raw data for like Google Square, did they exempt kids who were going to like private schools, or did they?
Their data were pretty rudimentary at the time. Yeah. Now people do. Now you can make assumptions for private schools. Now what ended up happening is that then changed, right? So I think back in the 60s and 70s, a lot has changed since then as a result of this, but back then, no. And again, that was one of the other issues is, and this is actually an issue that we look at now that's really hard, is that a lot of data, when you look at things like enrollment prediction modeling, all that, are done at very large levels, like the geographic blocks, and getting it down to small units or is difficult to do. So no, it was just census data, mostly back then.
So what if, like, within a county, it was predominantly like economic, you have 2 counties next to each other, but one was economically much better off than another one, and as a result, you had kind of a socioeconomic separation between race and force. How would you deal with the segregation that happened there?
That is what, I'll show you in a couple slides exactly that. And that is really, especially it's also the way you get around the legal challenges of not being able to use race, is being able to come up with ways that integrate schools based on economics. Because A, it helps you integrate your schools. B, it allows your schools to have resources. You know, one of the things we're doing in Evanston is our PTA equity project, because even the PTA funds are so different across schools. So how do you start to address those inequities? So yeah, I would say if you think about what are new trends in using optimization to look at school district, now looking at socioeconomic or economic. Really critical.
Yeah, just a detail. Previous slide, number
Yeah.
16, I think it was, track B was divided by a vertical line
Yeah.
between different races. Was that actually the case?
No, oh gosh, those were just stylized cases. No. These are, this here, this is just, no.
Right, but
Yeah.
it went so far as put the centroid of each
Yeah.
race was
Yeah.
track, presuming that it had physical meaning.
Yes. No, but this was just to illustrate the point. That's not a real school district. Yeah. Yep. Good. Other questions? No? Okay, so that's kind of, and I think that this case is really impressive to see what they were able to do, even with their solution methods that I think are somewhat flawed, really be able to argue on behalf of the plaintiffs to say there are feasible solutions to achieve this. So what have we done now in recent years? So there's been obviously a lot of work on being able to solve the integer version of it. So presumably you don't want to split neighborhoods. You want to say this neighborhood goes to this school. And so now you can take those xij variables and you can make them integer, these binary. You go here, you don't go here. That's been a big advance in solving these problems. What that also allows us to do, and if you combine that with new information, I mean, talking about getting just the population data, geographic data wasn't very good back then. It was much harder to integrate the GIS data with the optimization models. There's a lot more work on that now. And so what you could also do is look at contiguity, and this is a big issue with political districting, is you want, I mean, this is what we're looking at Evanston now, is how do you address the Willard Island, right? You really want your school neighborhoods to be contiguous. You want everyone who attends that school to feel like they're going to their neighborhood school. You couldn't really model contiguity back when you had the continuous variables. Once the variables are integer and you're saying I'm a binary variable, this neighborhood goes to this school, now you can start to think about ways to model this within an optimization model. Whereas before you just kind of relied on the dij squared to create regions that were compact, now we have ways to explicitly model contiguity. The second one is really what's done a lot in the political districting is you create flows. So you basically, if I take any block, and again, this is because we're going to start with much smaller blocks, so our going from a census tract to just a street block is our decision unit. And I want to make sure from any decision block or any of these units within my school, is there a continuous path to the school such that I'm only going to blocks that are assigned to the school? That make sense? So they're harder to solve. This makes the problem blow up, but we're pretty good at that. We can come up with ways to make that not so bad. And this is the point to your question before. So there's also papers now that are moving to ways to think about looking at median household income of blocks. So that becomes how do you balance? One of the things that I think is interesting is looking at ways to distribute Title I funding throughout schools in your district that are Title I funding. That, as an objective function, inherently creates balance. So the way Title I funding is if 40% of the students in your school or more receive free or reduced lunch. So if you take an objective function that says I want to maximize the number of schools in my district that are Title I funded eligible, that tends to have the effect of income distribution throughout. Because once you hit 40%, there's no advantage to go to 41%. And now I want to think about creating another school. Maybe that's at 35, and how do I go up? So it's a way to kind of, it's not a perfect proxy, but it's one way to look at that. So this is Evanston. I've got a few minutes, and then and still keep asking questions throughout. I appreciate that. This is Evanston. As I mentioned, kind of the challenge that we really face is the issue of the fifth ward, right? So there are tremendous advantages to being able to walk to your school, as I'm sure you can imagine. And so thinking about how do we address disparity in transportation in the district. So one of the interesting things, so this work, as I said, is sponsored by National Science Foundation. And so as part of, how many of you have been REUs in your past? That's it. It's all the REUs here. So there's the REU for NSF is research experience for undergraduates. There's also a thing called an RET. Does anyone know what that is? I didn't know what that was before now. It's research experience with teachers. So if you have an NSF grant, you can get a supplement to bring in teachers. And so we have 2 teachers from the district who have been working with us. And so what they did is they created a unit on bus transportation to be taught in a 4th grade class. So one of the teachers teaches this class, and she had them, so it is Washington School right here. So Washington is actually a pretty compact school, right? So everyone who goes to Washington lives pretty close. But Washington has a 2-way immersion program. So 2-way immersion is, we have a lot of English language learners in the district, and so one of the ways that you could, so we have ESL classes, but we also do 2-way immersion. So these are classes that are taught half in English and half in Spanish. And that's a really, well, I'll talk about that in a minute. But anyway, so Washington School is a 2-way immersion class. So what the teacher did is she printed out all of the bus routes at Washington School, and the students were going to look at mapping the routes and using some 4th grade math to think about the distance and the different statistics on the route. But she had them do a histogram first. And she asked them what time they woke up for school. Now again, Washington, for the most part, students do not bus for distance. They don't even bus for hazards. Most of the students who are bused to Washington are because they're enrolled in TWE, and most of them are the Spanish dominant. So the class is half English dominant, half Spanish dominant. Most were the Spanish dominant. So the students were looking at the data and saying, I think there's a big bias in what time you have to wake up for school based on whether or not your family speaks Spanish at home. So the way that the students are starting to think about transportation through an equity lens, the way that the school district is starting to think about transportation through an equity lens, I think gives us a lot of ways to think about how do we come up with the mathematical models to support that. And so one of the things that we're looking at are things like the placement of the TWE programs. Right? So when we think about where we place TWE across the schools, how do we use that to think about equity in bus transportation? It's a really hard operations class, or operations problem to solve, because like I said, you've got these 2 small strands. And so you're trying to hit pretty small numbers and keep them consistent, and that's really hard, and that's one of the things. Yep?
What was the reasoning for choosing Washington as the
There's a bunch of them. There are about 4 schools. But one of the things that they look at now, replacing new TWE programs, is where is the growing population of Spanish dominant students. So, and TWE has or Washington already has students who live close, but it's also a much further drive. Yeah. But that's what they're doing now, and this is, well, I can talk for hours about this, but thinking about instead putting more strands in the magnet school for TWE, which has pros and cons. It makes the bus routes more efficient, but again, the students who are participating in TWE are now traveling farther. So, other questions? No? So what the district is really interested in is how do we think about the way the students in the 5th ward are going to different schools, and can we think about ways to make transportation more equitable? So this is some of the stuff that the undergrads, I said if I had some time I'd show you what they're doing. So this is thinking about different places to put strands of the TWE program. So this is a map of the district, and what you can then do, this is, I just think, really neat. One of our computer science students did is you can now interact with the tool, and you can hover over a school and see how many students are participating in TWE, how many students are free and reduced lunch. You can also think about what is the resulting solution. These are highly multi-objective problems, so the user can think about, well, how much value do I want to put on different objectives? I can put no value on it at all, or I can move up, and it'll tell you how is your solution relative to the best that you can do. And so this is kind of some of the fun work that they're doing. But I promised I would leave time for some questions, so I would like to open it up for questions.